NumPy, SciPy usually get the most attention because they're used by a lot of people. But high performance computing with Python is so important because for those of us who are addicted to Python, you want an easy switch to move from pure Python to high performance computing. And PyOpenCL and PyCUDA have long been awesome packages. They continue to be so. And he has put in a lot of time, a lot of effort to make all of these packages outstanding. He is also a researcher in applied mathematics, scientific computing, computer science. He's a faculty member at University of Illinois at the computer science department. And most important of all, he's an extremely nice person. So it's very easy to get along with. You must have all noticed that, he's so approachable. So he's really helpful. That's really, really important, considering the amount of achievement. And if you go check out his software page, you'll lose track. You can't count on two hands all the number of software packages he's made of it. So we are really honored and pleased to have Andreas be with us here, spend the entire duration of the conference with us, and give us an awesome tutorial and an awesome talk. Thank you very much.
That's better. All right. Well, hi again. It's me, Andreas. And this is more stuff on how to make Python go fast. And for those of you who were there for the tutorial yesterday, what this talk is supposed to do is, well, be less about, explain how to do things and more explain why this is a good idea and why we're headed in that direction. And again, it's a similar theme, right? So we'll try and generate code, have Python be the controlling language, and do whatever bizarre hardware we've got to do the actual hard work. Before I get started, I'd like to thank, first of all, you all for being here, Prabhu and the Fossey team for inviting me. I'm enjoying this a great deal. I'm enjoying being around you guys. Also, the people who have helped make this happen over the years, Tim Warburton and Jan Esthaven, were two people who continue to be influential in my work. And Lucas Wilcox specifically has helped me flesh out some of the details of Loopy and other software packages. Leslie Greengard, my postdoc advisor at NYU, didn't mind me too much going off doing high performance stuff, when really he wanted me to do integral equation work. Then also, obviously, all the people who have contributed to the software over time. Without them, most of this would never have happened. Also perhaps as full disclosure, a couple hardware companies have been good to me over the years, so I would like to acknowledge them as well. Speaking of hardware, it looks like, this would be paradise in terms of getting code to run on computers. Every year, or even every half year, a new major chip comes out from, well, the big three companies that are making chips that are relevant in high-performance computing right now: Intel, AMD, and NVIDIA, right? And every year, on average, each of them puts out a new chip. And so if you're looking at each of these, tiny little pictures, what you have to think is one or more billions of dollars in development effort, right? So this is serious business, and all with the objective of making our computing experience better. And the way to make computing experience better is really either to make computers use less power for what they do, or to make them go faster, right? And the time what these chips do is achieve both. So this would be paradise, right? We all should be happy. in terms of our codes getting faster and using less battery and all of that. Now, be honest. When's the last time you've had that experience? Like, bought a new computer, took all your from your old computer, put it on the new one, boom. Goes faster. No. My actually last experience with that, my last laptop before that one, I bought in 2010. That was what Intel called a Sandy Bridge generation or second generation core or whatever laptop. And this thing that's sitting right there is what Intel calls Broadwell or fifth generation or something. And on a real per time unit performance basis, this guy is slower than my last laptop. Just a pat, right? So in terms of this picture, right, lots and lots and lots of new hardware. If you do single-threaded, if you write single-threaded code, it's actually going slower. So that's a little depressing, right? I mean, okay, I'll acknowledge it uses a lot less battery, and I appreciate that, but it's actually getting slower. And that can't completely be true, right? Because it's a new generation of hardware, and it would be kind of embarrassing if it was actually slower. So the depressing fact is, in order to actually squeeze all the performance out of that machine, you've got to do something different. And today, in comparison with the tutorial, today I want to be explaining what that is and what the physics behind that is. And you saw some of the tools. I want to elaborate more on what they can actually do if you take them all the way to the limit of their capabilities. And so in this situation where you have hardware that's getting faster, but in this kind of peculiar way, you can do one of two things. You can either roll over, say, okay, fine, I'll take what I can get in terms of performance, or you can say, let's try harder. And this is what this talk is about. What would happen if you really, really wanted all that the chip has to offer, right? And so that's also the reason this let's try harder. Let's try as much as we can to get what we can get. That means things may look a little bizarre and may look a little bit different from what you have seen in your intro computer science and computing class, right? You've seen this slide here yesterday, and I just figured I'd repeat it. When we say, go to high performance, make stuff go real fast, then what my opinion is that you should approach it with at least a little bit of a scientific ambition to understand what's going on, to see how much you can get, and to evaluate the performance of your code in terms of peak machine capability. And that means the statements that you can make have to be reproducible, they have to make sense, and they must apply on a broader scale than just you in that chair right now. Right, and the tools that I'm going to show are intended to help this cycle. So this is that same picture that you saw at the tail end over there. This guy, that's the chip that's in my laptop, just blown up a little bigger. And what we're going to try and do is first understand what's happening that's behind this, real performance loss per core. So this chip looks pretty, lots of fun colors, but it only starts making sense what's happening here if we mark up what the individual parts are. So the pieces where the code runs that, you start from the command line, like the Python interpreter or NumPy, those are these things here, right? There are 4 little cores here, and then there's a whole thing over here that's labeled graphics. But the graphics label is a little misleading, because what it really is a pretty big vector process. As in, it's like some smaller pieces of the course. This whole stupid thing is designed to do floating point math really, 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 really fast. And another thing that you can notice if you look at this over time, I'll just zap back. Oops. Where did it go? Yeah. If you look at this over time, and I just have one past generation of Intel hardware here, this is the vector part on the last chip. This here is the vector part on the current chip. It seems to be that these cores are getting smaller in comparison to the whole chip, and that the vector part is getting bigger. That's actually a coincidence. And we'll get into the reason for that in just a second. But in the grand scheme of things, what's actually true is just throwing more area at these cores, at the regular CPU cores, is just a losing battle. In the sense that you just can't extract more performance from them, no matter how much more area you were to throw at them. And that's why much more of the chip area is just headed in the direction where it actually makes sense. And that's why this chip ends up looking like, oh, there's a couple piddly cores over here, and then there's this massive hunk of vector hardware. So it seems like, just from the point of view of this picture, that it's something that seems to be here to stay, and something that we're gonna have to deal with it on some level, just as the computing community as a whole. Now, that begs the question: how do we make this kind of bizarre-looking hardware like our code, right? And this being SciPy India, the answer is obviously Python. But that doesn't make any sense because scripting languages are, I don't know, not fast, right? Whoops. So using Python for high performance, how on earth does that make sense? Well, the way that it makes sense for me is to think of a computation as really multiple stages. Obviously, the thing that you think about at the very tail end is the code that actually makes it happen. But there's a lot of stuff that actually happens before and around that, like organize the computation, which is to say this bit of data goes from here into that major computational block, and memory needs to be allocated. There's I/O and stuff. Then somebody needs to write the code, and before somebody writes the code, somebody needs to think about what actually needs to happen. And the approach that I'm suggesting here is that for everything but this last bit, we use Python, where we'll actually have Python help us write this bizarre, complicated code that we need to write in order to go fast on this hardware. And then this last thing we'll hand off to OpenCL, which is this little logo over here. And I'll explain in a second why that's where I'm headed. But just briefly, let me just say what OpenCL is. So OpenCL claims to be an open royalty-free standard for general-purpose parallel computing or programming across CPUs, GPUs, and other processors. So it's like the kitchen sink. If you've got floating point hardware on your computer, you can talk to it through OpenCL. It doesn't, as it proclaims itself, it doesn't really care what you're targeting, whether it's a GPU, a CPU, this vector thing that I pointed at on the chip picture. It doesn't care who made it, unlike some of the competing standards. And one particularly nice thing for the type of computational layout that I described is it has just-in-time compilation built right into the standard, so there's no grotty hacks that you might need to incorporate if you're wanting to generate it. So it's very amenable to that. It consists of two things. It consists of sort of an interface that you can talk to from Python, from the host side really, to make a computation happen. And it consists of a device-side programming language that's essentially. Now, OpenCL, as a thing, may or may not be here to stay. It feels like it might be because a lot of resources are being thrown at it, but you never know. The reason why I'm telling you about it is less that it itself is important, but sort of the abstract idea behind it is sound. As in, as you'll just see in a second, it has some kind of abstract notion, abstract model of what these machines look like. Obviously, there's lots of architecture-specific nonsense, lots of minutia that you could know, but there's sort of a 30,000-foot view of a device that actually applies pretty broadly, and it applies to modern GPUs, CPUs, no matter what, right? So that means you can't just, if you have code that targets this, you can run it on all those devices. It may or may not go fast, but it'll run. And you get the same notion of correctness across devices, which is at least one big step, right? So And obviously, there are lots of competing standards. So this guy, CUDA, targets GPUs by one specific vendor. And there's another thing out of Intel called ISPC. They all have exactly that same machine model. Right? They have the same abstract idea of what the machine looks like. They're just different spellings of the same thing, really. So in that sense, I'm pretty comfortable with this abstract idea of a machine sticking around. And that's why I'm telling you about it. Another thing that it is it's a low level. It's a relatively low level model of the machine. That means you have a relatively direct picture of what actually goes on with the code that you write. And that's important because if you're trying to understand what the performance is like, then you need to know what's going on, right? You're in the business of knowing what's going on. And on the basis of that, if it's not a low-level abstraction, like if there's a lot of if there are a lot of conceptual steps between the code that you write and the code that actually executes, then you have this problem of needing to psychoanalyze this gigantic tower of abstractions that may be going on between what you write and what actually executes. And that makes it really, really hard to understand what's happening. Whereas if it's a relatively razor-thin thing that just makes some irrelevant details disappear, but not too many, then you have a better chance of actually understanding and seeing what's happening. So I've sort of hinted at there being a physical, like as in physics, reason for all this happening. What might that be? Well, it turns out it is really just physics. And the physics that's behind this is actually not complicated, right? So if you think about what computers do, they actually have really kind of just two main purposes. Purpose one is to move data around, and purpose two is do bit fiddly computations with this data. Which of the two do you think is the actually hard thing? I guess the slide sort of gives it away, right? So why is moving data nowadays the expensive thing? Why is just doing the computation so super cheap? Well, if you think back to the picture of that chip, right, you can't see the individual transistors, but if you sort of compare in your head how big the core was in the previous generation on the Haswell chips and on the Broadwell chips, it just keeps shrinking, right? It's about the same amount of hardware, but it takes up less of the chip, right? So throwing more transistors at the problem, and the transistors are what make the computation happen, throwing more transistors at the problem appears to be not that difficult, right? The feature sizes on the chips that shrink and shrink and shrink and shrink. That means we can afford to throw lots and lots of transistors at floating point math or whatever it is. So computation is cheap. But in order to do meaningful computation, you've got to move the data to that transistor and back out. And this is where physics comes in. Currently, we move data through wire, right? Like if you want data from here to there, that means you need some sort of wire, maybe with a bunch of stuff in the middle, but you need a wire from here to there. And in order to get a signal from, say, this end to the wire to that end of the wire, what you effectively need to do is counteract a resistive effect of the wire and charge up that wire so that the voltage on the other end increases to a point that it's measurable over there, right? And the thing that slows this down is that the wire acts as a capacitor against ground. So it's really like a process like you might have seen in your physics classes. You're charging up a transistor. You're charging up a capacitor. And, well, if you want to do that, and obviously you want to do that fast because you want to transmit information fast, you've really got two options. Your option one is you just pump a lot of current in over here, right? Then that means you get lots of charge in that capacitor relatively quickly, but then that means, that laptop or whatever it is in your lab is going to run very hot. It's going to use a lot of power, which is a bad thing. Or you can wait, right? Just do a slow trickle of charge, and that means you're going to get less charge, and you're going to need to wait a longer time until this capacitor is charged. And so you're really stuck in this rock and hard place situation, it's either use a lot of power or wait a long time, or both, right? So that's really the main challenge that computers are up against, that moving data from A to B is expensive in either power or time, right? So that's the problem that computers need to solve. Now, that seems bad, right? Because that's basically what we're in the business of doing all the time, moving data between memory and where the computation actually happens. And so if you're in this situation and you have code that looks like what you write, in C, single-threaded C or Python, then you're executing along happily until you say urgently need some data that sits off in memory way over here. At which point, you, the processor, need to go and tell that memory chip way over there through that long wire, hey, that's the data that I need. Then this whole process that I described happens, right? You need signaling, and the memory chip, after a while, realizes time passes, and you, the processor, can't really do any calculation in that intervening period because, well, you need that piece of data to continue, right? So that the memory chip realizes, okay, here's what you wanted, here you go. And the more time passes, the signaling happens in the backward direction, and oh, hey, look, you're ready. And you can continue computing. That's obviously not a happy picture, right? Because that intervening period over here has not done any useful work. So if you're designing a piece of hardware that's really targeted at long sequential workloads, that's a scenario that you want to avoid at all costs. And that's partly to make workloads like this happy. That's what a lot of hardware in regular cores gets thrown at. But it's actually, for a lot of the stuff that we care about in scientific computing, it's not necessary to be in this situation, right? Because say if you apply a numpy operation, most of the time, say what you do to the first entry of the array doesn't depend on what's happening on the next entry of the array. So that all this could, in principle, happen concurrently. The thing that's really missing is the programming model that tells the processor, you know what, if you are in that situation where you're starting to wait on memory, just go and do something else instead, right? But if the processor knows that, then it can just go, hey, look, we'll just start working on the next thing until that hits a wait for memory, and can, from there, start on the next thing, and the next thing, and the next thing, and oh, look, by that point, the first thing might be ready, so we can jump back to that. And the happy thing is, in this view of the world, if we've given the processor a way to deal with the latency that we encounter from waiting for memory, then we're actually keeping the hardware busy the whole time. There's no big gap in the computation, right? And so this is really what all of this is about, right? Expressing to the processor right from the get-go, this is a pile of stuff that you can do in any order, right? And so you might look at that and think, well, I know what that is. That's called parallel programming. And really, if you think about it, it's not really parallel. This is kind of a subtle distinction. This is called concurrent because what really matters is that you make no assumptions about the order in which these operations are carried out, right? There's actually nothing going on in parallel here just yet. If you look, this is all one after the other. Just the order that it happens in is unspecified. And as soon as you have that promise of, I don't care about the order in which you do this big zoo of stuff, then you can also use that to throw some actual parallelism at the problem. So both this mechanism that helps you deal with latency and parallel computing use that promise of I don't care about the order in which you do this stuff, right? This promise of concurrency, which just means like this can all happen concurrently or any which way that you care to execute it, right? So as soon as we're in that situation where we've added concurrency, at just the lowest level, within one core, right? This move that I described over here is just intended to keep one single core busy, right? There's no multi-core, no anything. But as soon as we have that, we can throw more parallelism at the problem by saying, hey, let's just have multiple of these cores that are in that situation, and then we can say, well, within each core, what can happen is we'll add multiple so-called functional units, as in like floating point units, that are all going to do the same thing in parallel on different data, but with sort of the same control, right? And then we get, in essence, what is OpenCL's machine model. So there's essentially two levels here, right? There's the level that's across from one core to the other, and then there's the level that's within each core. And the level within each core has two purposes. One, it's to parallelize across the SIMD lanes, the vector lanes. And the second purpose is exactly this, the latency avoidance, right? So that's sort of the big picture. And we have these two levels, across cores and within cores, where the within cores thing has two different purposes. Okay. Now, if we needed to turn that into, right, like I said, inside a core and across it. If we needed to turn that into a programming model, how would that work? Well, the hardware that we've got, again, looks like this. There's lots of little cores, and the cores have, again, a bunch of floating point hardware, say 8 or 16 or however many, attached to them that are going to all carry out the same operation. And we need to abstract that just a little to make it programmable. How could we do that? Well, concretely, the first thing that we might need to know is, well, how many cores do we have, right? The second thing that we might need to know is how many of these vector lanes do we have? But really, those are details that don't quite matter, right? So ideally, or well, kind of predictably, that's the thing that's going to change between hardware generations, how many of those cores there are, how many of these vector lanes there are. So why don't we just make that go away as a detail? And instead pretend that, there's infinitely many of those cores, and similarly, that there's infinitely many of those vector lanes, because if we are in that situation, if we express our calculation with the idea basically as many as we can fill cores available and as many as we can fill vector lanes available, then breaking it back down so that it executes on a given set of actually finite hardware, that's not hard, right? Because taking a parallel program onto sequential hardware, not a problem. You just do one thing after the other. It's going the other way that's hard, right? If you have a sequential program, making that parallel, well, compiler vendors have been at it for, 50 years? And it's not really been a home run, so we might not be well advised to wait for that. So really, what this model targets is throwing all the parallelism, all the concurrency that we can get at it, and just wait for the compute abstraction to reduce it down so it fits onto the hardware that we've got, right? So how might that look? Well, the thing that's exposed to the programmer is a little bizarre, but it actually makes sense when you think about it for a bit. It's grid, and it's a grid that allows actually. Was there a question? Okay. It's a grid that has these two levels to it that I described, where the outer level of the grid targets the across core parallelism. Those are the fat lines here, right? So they're little groups that are all the same size, and one of those groups is going to go onto one core, and then there's more structure within each group, and that's the structure that's going to go onto the vector lanes within each group, right? So this here is the actually finite hardware, and this is hey, I'm just going to I'm going to use a grid to fit my calculation, and actually then I can have two-dimensional grids or three-dimensional grids just so if it's convenient for me, right? So if I'm doing image processing, I might use a two-dimensional grid just because it's convenient. And then the hardware is in the business of breaking that down onto just a linear core and vector lane index, right? So what might happen is in taking this grid with a function that runs at on each cell of these grids down to the hardware. And again, this here is a group, and each individual thing in OpenCL speak gets to be called a work item, or if you want, you can call it a thread, although that's kind of iffy in terms of terminology. Then what you might do is, well, you take the first group, you stick it onto the first core. You take the next group, stick it onto the next core. You keep going until you ran out of cores. And then you set each of these cores going. So you take the first however many vector lanes you've got. In this case, we've got 8 vector lanes. So you carve out the first 8 of these little items and map them onto the 8 vector lanes that you've got available. Then the next 8, then the next 8, then until you're done, right? So all that this grid provides is sort of a pile of concurrency for the hardware to draw from, and it then breaks it down to exactly how much hardware there is practically available, right? And then, once you're done with that, you go and take the next bunch of groups and map them to the next batch of cores and so on. Okay, right. With that in mind, how would you practically talk to such a thing? Well, the thing that makes that plausible and doable from Python is called OpenCL. And from yesterday, just showed you a brief demo of what that might look like. So I'm just going to go ahead and show you. So we're just going to do something super simple, which is there's an array of random numbers, and we're just going to double each entry to that inside of there. So not really hard, but it just serves to illustrate the purpose. Actually, hang on. Okay. Right. So to start out, you import a bunch of stuff. So there's OpenCL. We import that as CL. Apparently, there's also something like an array, like a NumPy array in OpenCL, just that it lives off on the GPU or whatever compute device you're talking to. And apparently, there's also a math package. So how would it all fit together? Well, let's say we take just like a relatively small array of random numbers that we cast to single precision floating point, and then we want to go to town. The first thing that you do is create what's called an OpenCL context. And the context is just a bag around all the stuff that goes with your calculations, programs, data. And when you do that, you get asked, well, here's a bunch of hardware that I found inside of your computer. Could be GPUs, could be CPUs. In this case, there's a bunch of things that I can talk to within my computer, and it gives me an option to choose. And I choose whatever hardware is convenient for me at this point. I'll just make a choice right here. And then the next thing to realize is the way that this all works is that the device operates kind of asynchronously from the main program running, which means I tell it a bunch of stuff that it needs to do, and it's going to do that in due time, but kind of not in sync with this program running. So the way that the structure that gives me a way to synchronize is called a queue. And as soon as I've got my context, I can create what's called a command queue in that context. And that's the thing that I can wait on that gives me a way to synchronize with the computation running off on the device. Next, I'm going to take my array of random numbers, this A guy up here, and I'll go and transfer it over to the device. That's relatively easy. So I'll do A device is cl.array.toDevice. So it understands what a NumPy array is. And within that queue that I just created, I say initiate a transfer from A onto the compute device. So what that does is it allocates the memory and it sets up that transfer. Okay. So So that's happened, and the thing that's actually underlying this is a lower level thing, which is just a bag of bytes. That's called a buffer inside of OpenCL. But from PyOpenCL's view, you can always usually operate from the view of the array, which looks much like an NumPy array. So that has a shape, it has a D type. Whoops, and I need to learn how to spell. It has all the things that you know and love in a NumPy array. It has strides. It has all that. Once I've got that, I can, remember our whole purpose in this was, let's do something simple. Let's just multiply an array of numbers by 2. So that I can do much more cheaply. I can just say 2 times device array, and that actually generates some code freshly for that computation and carries it out. But I actually want to go and show you what might be behind that, right? How might you do that if you didn't want to use this automation, right? So what would you have to write? Well, you'd have to write a tiny bit of C, and that tiny bit of C looks like this. So if you ignore these two kind of funny-looking words, if you ignore that there's this kernel and this global, it's really just a bit of C, right? You void twice. You have a pointer to a float pointer A, and then comes a thing that's kind of special, right? So what we're trying to do is apply this calculation down here, which is A is 2 times A, to a whole array. So what you'd expect is a for loop. But a for loop is kind of sequential, because you say, well, do this, next round do that, next round do that. So instead of doing a for loop, what we do is we tell the device, do exactly this, 50 to 50,000 times to 50,000 things individually. Each of these individual things can actually ask, well, what index am I? And that's what I can get from this function here, get global ID. In this case, it's a 1D. It's a 1D kind of grid. So I just ask along the 0th axis what my index is, and it tells me, and then I know where I am in that big computational grid, and inside of there I can then just do my work and I quit. So from a programmer's point of view, this looks horrifically inefficient, right? Because you wouldn't write a whole function to do just one bit of work. That seems totally silly. But the thing to wrap your head around is that that's actually a pretty efficient way to go about it in GPU land or in OpenCL land, because you're really intended to expose all of the concurrency that there is, and in this case, there is 50,000 times the concurrency. It really doesn't matter which array element gets operated on in what sequence, in what order, and so we tell it, here's 50,000 things, do them in any order, tell me when you're done. Right? So this is actually very efficient. And the overhead in getting this function to start is very low. So it looks like from a C point of view, it looks inefficient, actually isn't. So okay, what we do is create a program with this source code in our context, and we build it. So there's actually a little C compiler that runs right behind this .build here. And let me put this little bit of junk back in, so you have to tell it that it's what's called a kernel, and this is in what's called global memory, but those are details that eventually just fade in the background. That's not really that important. And then I can go and just run that. So my program now has an attribute called twice, and whoops, what just happened? Again? Oh, okay. Right, so my program now has an attribute called twice, right? And that's apparently a PyOpenCL kernel. So that's one of those object thingies. And that's the thing I can call. So I just go inside of my queue, that was that synchronization structure, call my kernel, and then I need to obviously tell the device how many of those little thready things it needs to start. Well, in Python, that's actually easy. We want one for every entry of the array. So we just say a.shape, and that's all we need to do. then we could also tell the device, what the sectioning off into little groups should be. But in this case, it really doesn't matter so much to us. So we can say, you device, figure it out for me. I don't care to deal with that. And then we need to tell it what data to operate on. So that's the buffer that's backing the device array. And that's all I needed to do. I get some synchronization structure back, and then I can go and transfer the result back and check that what I got was actually the correct thing. So I'll make a numpy array that looks just like A, and I copy the result back. So that goes in Q, copy. Or actually, no, since it's a device array, it's actually much simpler. I just do a device.get, and what that does is it takes the device array and copies it back to a numpy array. And then once I've got the result, I can compare it to 2 times A, and result minus 2 times A, and that's a bunch of zeros. So that did what it was advertised to do. Right. So that's a glimpse of what talking to a device might look like. And now you might go and think about this and say, well, that's fantastic for really simple kinds of calculations, like the idiotic thing that we just did, which is double a bunch of numbers. Unfortunately, lots of things are not quite as simple, right? They actually have dependencies across arrays, and so what can we say about computations that are more complicated than that? Oh, here's a slide about OpenCL. Here's the URL for it. Lots of people have downloaded it and have been overwhelmed with all the interest that it's got. It's open source and it's got a bunch of other nice stuff in it. But so how do we do something that has a more complicated dependency structure? Not just one input corresponds to one output, but really something that has a more global coupling. And the one key thing to make that happen is an algorithm called a scan or a prefix sum. And what that does is, well, in NumPy terms, it's really easy to understand. So I might have an array, random, I don't know, 20 numbers between 0 and 8, cast them to integers. So this is what my array looks like. And when I say scan or prefix sum, what that's supposed to be is really, there's a NumPy function for it this year. So think here, this is the first entry, that's 4. Then the next entry is the sum of 4 and 7. The next entry after that is the sum of 4 and 7 and 0. The next entry after that is the sum of 4, 7, 0, 1, and so on and so forth. And this is actually a very important operation. For example, if you have an array of things that are all producing variable size output, right? Not just constant size, but variable size, then this is something that you can use to figure out where in a long linear memory space to put your output, right? But if all you've got is like grids and arrays as a computational abstraction, then computing an output index or computing an input index is actually one of the more important operations that you've got, and the prefix sum is just what the doctor ordered, right? So then the computational, the dependency graph of that's behind that might look like this, right? So the first entry is the sum of these two, and the next entry is the sum of those two. And if you wanted to be efficient, then you'd compute the sum of the first two, the sum of the next two, the sum of the next two, and so on, and you'd have your result. Unfortunately, in this graph is embodied the fact that you're doing this one after the other after the other. It doesn't really look like it has a way to be parallel at all, right? Which looks unfortunate, but it's also one of the more interesting operations that you might have available to you. So, is there a way to make this more parallel? Turns out there actually is. And in order to do exactly that, what we'll do, we'll look at the math properties of what we're doing, which is addition. And we realized that addition is associative and commutative. And if we think a little bit more carefully about what we need to do, then we can lay out that computation like this. And if you trace back all the arrows, then you see, oh, actually, it's the same cells that contribute to all the same output cells, right? So this cell here has, in the first round, just these two summed into it. This cell has this guy and that guy summed into it, and so on and so forth. And then we increase sort of the step width and leave out more and more cells at the beginning. And at the end, so this guy, for example, has the sum of everybody that came before it. Now, if you think about this a little bit more carefully, you'll realize that that's actually way more carrying out way more operations than this layout of the computation. But this actually has the ability to be executed in parallel, and even though it's more work, it's actually way faster. And that's often a trade-off that you have to do. You have to do more work in order to get there faster, which is bizarre, but in terms of what the hardware can do, that's actually what ends up being necessary, right? So a lot of these additions are redundant, but we'll do them anyway. And if we do that, then we're done for this size of array in just well, in this case, it's log of how many array cells we've got. So here, that's 1, 2, 3, 4 operations, rather than however many cells there are. So it goes from order n to order log n. In terms of parallel steps. Right, okay, so that will be nice to have, and it turns out if you need something like that, then you don't need to look too far. So in addition to making OpenCL as a thing available to you, you can, what PyOpenCL also has is algorithms like that built in. And it has that, oops, all right, start that then. Hasn't even started. What's going on? Start that. Sorry about that. 1 second. Okay. Right. So same general setup as we did before. We import PyOpenCL. We create a context and a command queue and an array full of random numbers. And really, the NumPy thing that, in NumPy terms, what we're trying to do is a prefix sum of the squares of the array. So nothing too terrible. And then, to make the same thing digestible to PyOpenCL, what we do is we create what PyOpenCL calls a generic scan kernel within the context. And then we just have to say what operation do we need, right? So we tell it our inputs. Our inputs are say an array y and an array x. And what we want to do is sum the squares. So upon input, we do xi times xi, which computes that square. Then the next thing says, what is the operation that we want to carry out as part of the scan? So that comes as a plus b, where a plus b are just symbolic equals for the two things that are getting operated on. And we need a neutral element, which is 0 for addition. So 0 plus a or a plus 0 just gives me a back. And then upon output, we stick that exact thing that came back from that calculation, that's again a symbolic variable called item, we stick that into y. So that makes it possible to do some processing on input, some processing on output, and it gives us a relative amount of flexibility to say what do we need to happen at all the intermediate steps, right? And PyOpenCL is then in the business of generating the code that implements that, right? So I go and do that, and again, convince you that it's actually doing that and clear the output. And I compare the output that I got from NumPy with the result that I got from PyOpenCL. And what's your comment on that? Is that good or is that bad? Well, if you think about what's happened, we've carried out our floating point operations in a different order, and it has no right to be exactly equal as soon as you reorder, because floating point math is actually not factually associative, and so that makes it fair that we've accumulated some amount of error, right, in reordering that calculation. But otherwise, it's done exactly that calculation, and it's done it a lot faster and actually in parallel. And so you can use PyOpenCL to get relatively complicated operations just based on that scan. So things that you can do with that include things like if you have a list and you just want to say, well, I want those entries of the list that satisfy a certain criterion. That can be implemented by a scan, because it's really just an index calculation of how many things satisfy the criterion and where do they go in the output. And if you keep thinking about that, then a sorting operation is also just really an index calculation, because what is sorting? It's really computing where something goes on the output, right? So all those things are available in PyOpenCL, built on the scan, and they're all pretty quick. Right. Okay. So that's what's in PyOpenCL. But then you already saw that yesterday. That some things you can, or rather, if you think about what PyOpenCL can do, it can help you automate some sort of cookie cutter operations like scan, like things that fit inside of a scan framework, or things that fit into a global sum framework, or things that fit into an element-wise framework. But for more complicated things, it really has a hard time just helping you write that code, especially if you're dealing with things like multidimensional arrays. And that's exactly where Loopy comes in, which is a tool to help you write these kernel codes and help you express them in a way where you express your mathematical needs. And then from there, it goes and gives you a bunch of knobs where you're in control of how the computation gets mapped onto the actual hardware. Right? So you first describe your computational intent, and then you describe exactly how you'd like that mapped onto the hardware, and those two things are strictly separated from each other. Right? So I showed you a little bit about Loopy yesterday, just as a very brief reminder. Oops. What I actually want to show you is some of the cooler things that it can do, but I just want to briefly remind you what it does. So, see, where are we at? The example that we saw yesterday, and I'm not going to go through all of it, I'm just going to show you, was this outer product, right? Cij is AI times Pj, and then we were able to say, well, do this with the I-axis, do that with the J-axis, prefetch some data, stuff like that. Once you've got that, then you are in a situation where you think about, okay, what's actually a good way? What's a way for me to lay out that calculation that the hardware may like? And if you're actually writing the code by hand, one of the unhappier things to come to realize at this point is, well, in order for this to go well onto the hardware, I actually need to change how things are stored. Because references to your data just occur all throughout calculation, so that means if how the data is stored is what you need to change, then you're in the business of dredging up your whole program and changing everything about it. So wouldn't it be nice if I could just have Loopy change how my data is accessed, where my math level view stays the same, but what gets implemented actually changes. So here's how that might look. Again, we're just going to import all the business, so PyOpenCL and Loopy. Create a context, nothing special. And this sample calculation I took from one of my codes. So what this does is, well, I write finite element codes. So there's this could be a D field, and this could be an electric field. And these things live on individual finite elements. On each finite element, I have a bunch of degrees of freedom. And within each degree of freedom, I have a number of XYZ components. and then I go, well, to compute the D field from the E field, I just want each of the E fields to be multiplied by a dielectric constant that's constant on each element. Right? Relatively simple calculation, and Loopy can just generate a kernel for me, no big deal. In this case, that's just a simple for loop thing. But something, if you start reading up on hardware, that you may realize relatively quickly is that this jump, like the thing that's most likely to be your axis of parallelization is this axis of degrees of freedom. And here, there's a jump of 3 from one to the other, to the next, right? And that actually happens to be a bad thing because it messes with your memory axis. It means there's gaps in the memory axis. So that you typically want to avoid that. And in order to avoid that, then you might need to change the data layout. And here in Loopy, I can just say, well, for example, change how my E field is stored by doing the first 2 axes in row major, as in C order, and by making the last axis be a separate array for each entry. Right? So that's what the step means over here. And otherwise, everything else stays much the same. And if we then look at the generated code, you can see, well, I need to zoom that out a little bit so that you can see, all of a sudden my E field has 3 individual arrays, and my degree of freedom all of a sudden is a stride 1 aspect. Right? So that's something that a normal compiler can't hope to do for you automatically because it involves changing how your data is stored, whereas in Loopy, because you're asking for it, you can make that happen without a problem. And it's something that leaves your original calculation statement the same. It's just with something that happens on the computation, right? Another kind of neat thing that you can do if you're meaning to adopt this kind of analytical way of thinking about performance, another need that you'll have fairly quickly is understanding how much work you've done in how short a time. And Loopy actually has a widget to help you deal with that too. So here's the same code as before, just A and B. And this is a simple matrix multiplication. So Cij is sum, K, Aik, Bkj. And what we're then wanting to do is understand, well, how many calculations do we carry out, right? And we can just ask Loopy, well, give me polynomials that represent how many operations I've done, and it comes back pretty instantaneously. It says, well, you've done n cubed additions on single precision floating point, and you've done n cubed multiplications on single precision floating point. And then, based on how you transform things, so here's some sort of bizarre transform. Or, well, the other thing that you can do is count however many things, however many memory, how many times you access memory. And here you can realize one of the key problems with implementing matrix multiplication. There's n cubed, 2 times n cubed loads, but only n squared stores. Right? So there's a little bit of a mismatch. And then you go, well, let me try and transform this a little. So you come up with a slightly optimized kernel, and you compute the number of operations in that. And things get a little bit more complicated. So here's the number of multiplications, and it's no longer really n cubed. It's got some idiotic index math caught up in it. But even in that case, you can get a relatively accurate view of how many operations you carry out. Okay, I'm almost done here. Just wanted to show you what you can get if you use this tool. So what I do for a living is solve partial differential equations. So many of the examples I show come sort of from that neck of the woods. And where the journey started for me is I did all these things that Loopy can do by hand, and it worked pretty well, but it was actually hard work, and I didn't want to do it again by hand. So that's what prompted me to write Loopy. And I actually, we've been through that just now. The things that it can do for you are well, here are 2 slides with just a big long list of stuff. It can unroll loops for you, it can prefetch, all that stuff. I'm not going to read it to you. Some things that I've recently added is, say you have two totally separate calculations, you can just mash them together into one and have them calculate in unison if they use the same data. That can actually be a big win, for example. Or it can vectorize, it can, in a somewhat intelligent way, deal with intermediate results. It can change your code so that it uses instruction level parallelism. It can use some math properties of what you're implementing. So it's become relatively versatile. And here are some sample calculations just of this year's vector addition with some scaling. And here we get relatively close to the bandwidth peaks across a bunch of different hardware. Similarly, for matrix multiplication, we're much more likely to be flop limited. And again, we get reasonably close to what can be done. This here is an n-body calculation, and just measured unfortunately not so much in hardware level, but really in the number of millions of pairs per second that we calculate. And these here are some finite element calculations back to being measured in gigaflops per second, and those numbers are even higher than the ones for the matrix multiplication. So that's sort of what it can do. A couple more things. It can check your code so that all your accesses are inbound. It can obviously generate a sequential version. It can do benchmarking for you. It can do testing for you. What it can also do, is kind of totally separate, but if you're into that kind of thing, it can read Fortran code and turn it into its kind of a program representation, and then you can use this in a way that you might use it. And here there's a bunch of comments that say, well, transform my, in this case, matrix multiplication according to some Loopy kernel. So it's kind of fake OpenMP kind of thing. We did that with one of our finite element kernels and compared it with something that Lucas Wilcox and Tim Warburton had done by hand. And we're actually able, by applying just this long string of transformations, to get within, spitting distance of the hand-tuned kernel, which I thought was really kind of nice. So there, that's basically it. To me, this is an exciting time to be in high-performance computing. There's a lot of stuff going on. Fortunately, and based on the physics, it all seems to be pointed in one direction, which is feed the hardware some concurrency, and it's going to figure it out. And some, the details are annoying and sometimes weirdly different between different pieces of hardware. But that's sort of the purpose of Loopy, to try and make those as much as possible. And GPUs and scripting languages don't seem like an obvious match in some sense, but if you adopt this view of code generation, it seems to work surprisingly well. And my hope for Loopy is that it's just general enough to do a broad cross-section of number crunching things that you might do. And something that I'm thinking about is, well, once we're in the business of understanding calculations, maybe if it understands shared memory so well, maybe in the future we can make it do distributed memory as well. If you're interested, come chat with me. All right, that's all I've got to say. Thank you so much. And if you have questions. Mm-hmm. There is. So the question was, in the scan, there is an amount of redundant calculation going on. And by introducing even more structure to the, I'll be there in just a second. Oh, well. Almost there. Right? There's a lot of sort of redundant calculation going on, and you can avoid a part of that by mixing how much you do sequentially with how much goes on in parallel. So you can actually do hybrids of this form and that form, but the code gets even more complicated, and actually PyOpenCL does that under the covers. So you can avoid parts of it, but it's not entirely avoidable. Does that answer your question?
Okay, so unfortunately, I think we don't have more time for questions.
Sorry.
But he's available all day, and we have lunch, tea, and 2 teas, so you can meet him afterwards and ask him any questions. So thank you very much for a wonderful talk. So our next speaker is Jared Millman, who, as you know, has helped start this whole conference. After many years, he's back with us again. Jared has an interesting history, as I said yesterday. He was an early contributor to SciPy. He helped organize many of the SciPy and NumPy releases. He also organized the SciPy US conferences, at least when it was held in Caltech for many years. He was director of computing for the Neuroscience Institute in Berkeley, which hired Fernando Perez at one point, pulled him out of physics, quantum chromodynamics, to neuroscience. And then he decided to quit it all and get back to what he wanted to do, which is biostatistics. And so today, he'll be talking to us about Python for statistics. He also conducts, so he was also the NumFocus, one of the founding members of the NumFocus group, which actually funds a lot of open source projects. And he also conducts every year a workshop or a mini symposium at the SIAM conferences every year or every 2 years on improving the state of computational science education. Sure. So, some technical glitches. So we'll start in a minute. So anyway, we're very happy to have him with us. We'll start it.
You would have to mount it manually, though. Yeah. Sorry about this. Earlier,
So if there's another question, take a minute to set up. We'll answer another question. Any more questions for Andreas? Have a question?
My question is not just regarding high performance computing, but it's regarding like generating C code and stuff using Python for even for writing drivers. Is it possible? Will it be optimal?
So the question was, generating C code from Python. In his application, if I understood that right, that was for writing device drivers, right? Is that possible? I would say sure. I mean, honestly, I want to basically shoot myself every time I have to write C by hand. So very often I just do, most often even just pretty unambitious things that help me write repetitive, boring code to write. So I'd encourage you to try. It's definitely possible. Whether it turns out to be a good idea is like that depends on the application. But one thing to watch for in general is something that if you're writing some automation to help you automate a tedious task,
Nothing to do with
then whoever takes over this code in the future has the problem of not just needing to understand what you were trying to do, but also this level of automation that you introduced, right? So that's sometimes a little bit of a burden, just because they might not get exactly what you were going for and what the original problem was that you were trying to make smaller. But all of those are solvable by being careful and by documenting what you're actually doing. So it's not, you know, it's not guaranteed to be successful, but if you're careful, it can be pretty rewarding. Does that answer your question?